Welcome back to the new session. In this session, we will be discussing about the Excess-3 code. In the previous session, we discussed about how we can perform the arithmetical operation with the BCD code. And we also try to understand different kind of binary codes that are needed in the computer systems. Okay, so let us talk about what is this Excess-3 code and how we can represent this Excess-3 code. Before that, I just wanted to discuss a few things about the Excess-3. And before that, we must know how the BCD code looks like and what are the importance of that one. Okay, so this is important. So let us try to write few things which are important. If you see in the BCD code, the total possibilities that we can accommodate is from 0 to 9. Okay, so these are the possibilities that we can accommodate in the BCD code. And if you try to write its binary equivalent or the BCD equivalent, that will be nothing. It is 0 0 0 0 2 1 0 0 1. Rest all other digits like from 1 0 1 0 to 1 1 1 1, they are invalid in the BCD code. Okay, so this is all about the BCD. Okay. So yeah, so this is the BCD. Now let us talk about what is the Excess-3 code. Okay, Excess-3 code, if we add +3 on the BCD code, which is 0 0 1 1, then it will become the Excess-3 code. Okay, why we are adding +3 and what is the importance of this Excess-3 code? If we have already this BCD code, I will tell you later on. Okay, so once we have added 0 0 1 1, this code will become the Excess-3 code. The name, like with this, its name, like you can say, if I have exceeded all the values with the 3, then that is why we are calling it Excess-3 code. Okay, so this is the simple thing. Now if I'm talking about the Excess-3 code, then the equivalent number for 0 will become 0 0 0 0 plus 0 0 1 1, that will become 0 0 1 1. And for 9, as we have in BCD 1 0 0 1, and I need to add 1 1, and after adding these things, I will get what? Can anyone comment what I will get? If I will add 1 0 0 1 plus 0 0 1 1, then what should be the Excess-3 code for 9?
Sir, 1 1 0 0.
Perfect. 1 1 0 0. 1 1 0 0 is the code for 9, and these codes are in the Excess-3 code. Now let me explain what is the reason why we are adding +3. If we can recall the BCD code in the previous class, we saw the BCD code is not the self-complementary code. Means 0 and 9 are not self-complementary. Okay, so to make the number self-complementary, we have to add +3. Now this is the homework. Now you can see 0 is complementary to 9 here. Okay, so the number becomes the self-complementary. So this is only just to add some features on the code. Okay, so to make the number self-complementary, you can use this Excess-3 code. Okay. And this is the advantage over the BCD code. Now one more important thing, as we can see in the BCD code, we had 6 invalid numbers. Okay, that was from 1 0 0 1 1 0 1 0 to 1 1 1 1. This was the invalid number. Similarly, because I'm considering this Excess-3 code is the extended version of this BCD code, so here again we will have 6 numbers which are invalid, but those numbers are not same as the BCD code. Can anyone comment which are the numbers which are invalid in the Excess-3 code? Which are the number which are invalid in the Excess-3 code?
13 to upper.
Okay.
So or we can say 0 1 2 3. 0 1 2.
Perfect. Yes, 0 1 2 3 and 13, 14, and 15 decimal equivalent. These all 6 numbers will be invalid in the Excess-3 code. Okay, so if I try to write this one, so 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0. This is from before 0, and after that we will have 1, 1, 0, 1, 1, 1, 1, 0, and 1, 1, 1, 1. So all these numbers are not valid in Excess-3. Okay, and we know that for BCD which are the numbers which are not valid. Okay, so this is how the Excess-3 code works. Like similarly, we had performed some additional addition operation and the subtraction operation with the help of BCD. And if we see the BCD, what are the different rules which we opted while performing some addition and subtraction? Those rules was, if some carry is generated from one nibble and that is transferred to the second nibble, I have to add +6 on that nibble. This was one first condition. And the second condition was, if the number is greater than 9, which is 1001, then I have to add +6 on that. So this was the condition if I am performing some BCD addition. Okay, similarly, because the Excess-3 code is the extended version of the BCD code, I have to follow the same. Okay, if the carry is generated, then I have to add 3. Okay, and if the number is greater than this one, then I have to add 6, and it is less than this one, then I have to add 3. So this is what I have to do. This is important, like how we can perform the equivalent Excess-3 addition and the subtraction. So I am leaving it to up to you. Just try to solve it just like what we did in the BCD code. And in case of any doubt, definitely we will consider that in the tutorial lecture. But I am giving you the time, like just you can consider any of the example, just like a BCD. Just try to add it and try to follow the same kind of regulations what we did for the BCD. But instead of 6, we have to deal with the 3 and then try to solve the answer. Okay. In case of any doubt, definitely we will try in the tutorial lecture. Okay. So the homework is like perform some Excess-3 addition, perform some Excess-3 subtraction, and then Excess-3 subtraction using 9's complement and Excess-3 subtraction using 10's complement. So this is the homework that you have to do at home. Okay, just like what we did for the BCD code, try it at home. Okay? So this is all about the Excess-3 code. One important thing about the Excess-3 code is, like this is one kind of the BCD code. Okay, and this is non-weighted code. Okay, because the weight of each digit is not decided, and this is only the sequential one. It starts from 0011 and that reach up to the 1100. Okay, so this is what we call it. It is a sequential one, but it is non-weighted. Okay, of course, this is the self-complementary. So this is the only advantage which we are getting out of the Excess-3 code, other than this BCD, is that we can make it the self-complementary. Okay, so these are something that we can do. So in summary, if we can say, the Excess-3 code is equal to BCD code plus 3 decimal. Okay, 3 decimal, or simply let me write 0011. So this is the key point that we should remember. Okay, so this is all about the BCD code. Now let us talk about the gray code, which we left in the previous class. Like I was talking about the cyclic code. Cyclic code means like suppose some code is like, before I start discussing about the gray code, let me tell you what the cyclic code is. Suppose I have a number, okay, something like 0 to 9, okay, and let us assume for 0 in some of the code, let us assume I have given like for 0 0 0, it is like this, 0 0 1 1 is treating as a 0, okay. If I am increasing by 1 with this code, like 0 to 1, if I'm going to 1, in that case I have to rotate it cyclically, like 0 0, let us assume I have rotated in the left direction, in the right direction, so it will become 0, this 1 will come in this side, so 1, this 0 will be here, this 0 will be here, and this 1 will be here. So 0 1 0 1 double 0 1 will be the code for 1. Similarly, if I'm trying to make it for 2, then again I have to rotate it, so this last one will come to the first, 1 1 0 0, and then for 3 it could be like 0 1 1 0. So the maximum possible symbol that is possible are like how many numbers of digit we have in the code. This is the maximum number of possible symbols that we can accommodate on it. Okay. Yeah, some questions. Only one bit will change. What is the reference to ask this question? Okay, okay, clear. Fine. So this is all about the gray code says. This cyclic code says. So cyclic code means like just we are making it cycle. Like we have started from 0 0 1 1, and then one bit will change it either in left direction or in the right direction, and accordingly we can. Okay, so this is how we can decide the code is cyclic code. It could be like.
Excuse me, sir.
Yeah, please.
So yesterday you said that that in cyclic code the bit only changes like once. So sir, from 0 to 1, the rightmost bit is 1, and in 1 also it is 1. But from the right, the second one is changing from 1 to 0, and the first bit, the leftmost bit, it is changing from 0 to 1. Sir, here it is changing twice.
No, I just told you like it. Yeah, I think I don't know. I cannot recall what I said yesterday. But the simple concept of the cyclic code is just whatever the code we have, just I have to rotate it by 1 bit. I have to change it by 1 bit, means in any one direction. This was the reference. Like if I'm changing by 1 bit in the left direction or in the right direction, that we call it a cyclic code. Okay. So this was a reference to say like 1 bit. It's not like, suppose I have a code for 0 is, let us assume it is 0 0 0 0, and for 1 it will become like 1 1 0 0. No, it is not true, because we are shifting 2 bits now here. Okay, we can shift only 1 bit in any one of the directions. So that this kind of codes we call it the cyclic code. Also, yeah, the gray code is the part of the cyclic code, like where we can say only 1 bit is changing. I will tell you about this gray code. Please wait. I understand what kind of questions you are asking. That is absolutely correct. Gray code is the part of the cyclic code where only 1 bit is changing, but this is not the necessary condition for the cyclic code. For the cyclic code, it should rotate something like that. Okay, it should change its position. Okay, but for gray code, like it is also following some cycling kind of pattern. How it is following and how 1 bit is changing. Let me finish this gray code, then you ask the question again, then I will answer that part. Okay, so then that your doubt will be perfectly clear. Please wait for some time. Okay, so let me start this gray code, and I will tell you what this gray code is and how we can use it. Okay, important point about this the gray code is it is non-weighted code. Okay, it is non-sequential code. It is not a BCD code. It does not follow the pattern just like a BCD. Okay, it is the unit distance code, and this was the reference which I just told yesterday. Like the gray code is the unit distance code, or the single digit, only single bit is changed. Okay, and this was the reference behind that. Okay, So the gray code is the unit distance code, means whatever the data we have or whatever the code I have for the 0, and if I'm making the code for 1, so only one digit must change. It is not necessary. Like if you see the binary pattern is like 0 0 0 0 0 0 1 0 0 0 1 1 0 0 1 1 is for 2. So if we can see here 0 0, I made a mistake. 0, I'm saying other thing, 0 0 0 1 and 0 0 1 0. So if you see like this in the binary, this is equivalent to 0, this is equivalent to 1, this is equivalent to 2. Here one bit is changing, but here the 2 bits are changing. So, but for the gray code, this kind of the property does not exist. Only one bit is changing. Okay, so this was the reference which I said yesterday. Okay, so let me finish it, then your doubt will be clear. No, don't worry. It is the reflective code. Okay, how we are calling it reflective code? There is a difference between reflective code and the self-complementary code. Okay, self-complementary and the reflective, these two are the different concepts. So because before I have never said like how we decide whether the code is self-reflective or not. So here I will tell you how we decide the code is reflective code. Okay, and it is a cyclic code. I will tell you how this gray code is following the cycling kind of pattern. Okay, and the important thing is the gray code cannot be utilized for the arithmetical operation. This is always utilized for the Boolean function reduction or the K-map. In the K-map, what is this K-map? I will tell you. So these are some points that must be considered before the gray code, before you start with the gray code. Now let us try to discuss one by one how we can calculate the gray code of any number, whatever we have. Suppose I have a decimal point. Okay, let us assume a decimal points are, let us assume 0, 1, 2, and 3. And if you talk about a binary equivalent of this decimal point, the binary equivalent is like 0, 0, 0, 1, 1, 0, and 1, 1. But as we know that the gray code is the unit distance code. Okay, so only one bit must be changed. So suppose I'm starting this gray code like if the gray code for the 0 0 is 0 is 0 0 and for 1 is 0 1. So if you see here only one bit is changing. So this is definitely, it is following the regulation whatever we had. Now suppose if I'm talking about this binary, if you see here 1 is changing, this bit is changing from 1 to 0 and this bit is changing from 1 to 0. So here 2 bits are changing. So this code is not valid for the gray. Okay, so for gray what we can do, either I can change this digit or I can change this digit. But if I will change, let us assume I am changing this digit. Okay, so if I am changing this digit, this will become 0 and this digit will be same, this will become 0. But this code is already exists for the 0 0, so I cannot change this code again. Okay, so I need to choose the different kind of digit where I can do, and I have to change this digit instead of this one. So if I'm choosing to change this digit, this 0 will become 1 and this 1 will be as it is like that. Okay, so this is how it can work. So 1 1, yeah, perfect, Jai. So 1 1 is here. Now if you see, again I need to change one more bit to get the code for 3. So I have a possibility that I can change this digit or I can change this digit. Okay, let us assume I'm changing this one, I'm changing this digit. So in that case, this 1 will become 0 and this 1 will be as it is. So, but this code is already exists for 1 0 for 1. So this is not valid. So I need to change the second one. So this will become 0 and this will become 1. And how this gray code works and how we can define the gray code. So this is the simple way to calculate the gray code. Simple thing is I have to consider a single digit that must be changed. So all the things are clear. Now only two things are left. How we are calling it the cyclic and how we are calling it the reflective. Okay, so let me explain these two things. Okay. Yes, here we have some patterns, something like that. Let us assume. Whatever the shades you are seeing here, like either in the green or brown or in the blue, this indicates logic high and white indicates logic 0. Okay, So let us try to see how we can understand about this gray code. The innermost circle, this innermost circle that indicates the most significant bit, whereas the outermost circle indicates the least significant bit. Okay. Now, if you see here, the gray code for, if I'm considering 3-bit gray code, then how the gray code will look like? Let us try to see here. Initially for 0, it is 0, 0, 0. For 1, it is 0, 0, 1. For 2, I need to change 1 bit. So, because I have to follow from right to left, so I have to change this digit. So 0, 1, 0 will be there. Then I have to change this one, 0, 1, 0. So this is what I am getting up to 0, 1, 2, 3. Okay. If I see here, if we see the most significant bit logic here is like, this is a logic high, which I'm giving it is, I'm treating it as a logic high. And this upper portion, which I have combined 4 digits, this is acting as a logic low. Now, if I have to make it cyclic, then what I have to do, I have to rotate this codes in the next phase or the next digit or the next digit. Like initially I'm considering the most significant bit, so I need to move in the right direction. So if I'm moving in the right direction, the next bit is moving something like this here. Okay, so this I am changing from 0, like I have rotated it by 90 degree. Okay, and again if I see the third one, I have rotated again the colored button with the some angle, so something like that. Like we are rotating the next bit with the cyclic form, so that is why we can call it the cyclic code. Now, how we can call it the reflective code? Let us try to see here. To justify this one, let us try to see here. I have if n1, then I have 2 digits 0 and 1. Okay, now what I am doing, I am just reflecting 0 and 1 as it is. So what I have 0 and 1 for n is equal to 1, I am just replacing it like this, and then whatever the number I have reflected it, and that becomes 1 and 0 here. Okay, so if I can reflect it from 0 and 1, then that will become 1, 0. Once we are ready with 0, 1, 1, 0, so this becomes this part, least significant bit part, and upper portion I will provide logic 0 and the lower portion I will provide logic 1, and that becomes the gray code for n is equal to 2. So that is how we are calling. Similarly, let us consider the n is equal to 3. Okay, for n is equal to 3, whatever the n is equal to 2 we got the results, we need to change, we need to write it as it is. And now after writing this, I have to reflect with this one. Okay, so what was at last, I need to replace it 1, 0, 1, 0, 1, 1 should be placed here, 0, 1 should be placed here, and 0, 0 place should be at the bottom. Okay, so this is how we can reflect it. Once we have reflected, and at the axis we have reflected, the upper portion will be provided 0 for the MSB and the lower portion will be provided logic 1 to the MSB, and that becomes the gray code for n is equal to 3. Okay, so that is how we are calling it the reflective code and the cyclic code, because it is following some pattern, it is rotating in some way. Okay, so this is all about the gray code for n is equal to 2, n is equal to 3, and so on. You can calculate something like that. Now the forum is open for 1 minute. If you have any doubt on this gray code, now your doubt is clear, what you said before. Who asked the question before about the cyclic code? Your doubt is clear now?
Yes, sir.
Fine. So
Can you please explain this cyclic part again, this figure?
okay.
But also reflective one also.
Reflective part. Okay, let me repeat it again. Okay. First, let me explain the reflective, then I will go back to the cyclic part. Okay. If I'm talking about the reflective code, see here, for n is equal to 1, we have a 2 digits 0 and 1. Okay. Now, if I have to make the gray code for n is equal to 2, In that case, what I have to do, whatever the digits we have for n is equal to 1, that I have to write it as it is. Like 0 and 1 was there, so I have written 0 on 1 here. Okay, once I have written 0 on 1 just like what we had for n is equal to 1, then make a axis and then reflect it. So what was at last, that will come first after reflection, and the 0 will come later on. So 1 and 0, that becomes the reflective. Okay, so now we have a 0 1 that comes from n is equal to 1, and this 1 0 that comes from the reflective property. Okay, because I have reflected this axis after this one. Okay, just put a mirror and then you will get the reflected kind of thing. Okay, so 0 1 1 0 will come. Now that becomes the least significant bit. Okay, so this is passed to the LSB side. Now once we are ready with the LSB, and the point where we have put it the mirror to make it reflective, just put the upper part as a logic 0 and the lower part as a logic 1, and the whole code will become the gray code for n is equal to 2. So this is how we can say. Similarly, if I'm talking about n is equal to 3, then whatever the number I got here for the n is equal to 2, that I have to replicate it as it is. Okay, and then I have to make the reflect. So this 1 0 will be here, 1 1 will come next, 0 1 will come next, and the 1 0 0 will come at the last. So this is how we can reflect this code. Once we have reflected this one, this number, whatever we got after reflection, that will become the LSB. This part will also become the LSB on the lower side. Okay, and now the upper part where we have reflected, just provide 0 0, and for the lower part provide 1 1, and that will become the gray code. So this is how we can say it is the reflective. Doubt is clear about the reflective? Who asked this question? Okay. So this is how the reflective code works. Still there is doubt, you need to acknowledge it whether you are getting the answer or not. Okay, so means for reflective we need to only change the value of MSB. Perfect. Yes, so for reflective the voice I'm not getting perfectly. There is some, you can write on the chat box if you have any doubt, right? So simply whatever like previous for the previous and whatever we got, that we have to reflect.
Clear.
Okay, fine. Please unmute yourself if you have told.
Clear.
Okay, please unmute. Yeah. Please mute yourself so that the noise should not come to us. Okay. Fine. Now let me discuss like how this the cyclic code looks like. Okay. So see here, if we talk about the most significant bit part here. So this most significant bit part is, this is logic 1, and the upper portion, this is logic 0. Okay. Whatever the logic we have, just what we did, just we have to get the gray code. I have just rotated this by some angle. Okay. So if I have rotated, then this will become something like this, 0 0 1 1 and something like this. So simply what I have to do, the simple thing is just you have to rotate the code. Whatever the code you have before, you have to rotate with the some angle. Okay, so you have to rotate with some angle, then you will get something like that. Okay, so before you have, like, let me consider it. Okay, so suppose initially I had the least significant bit 0 1 1 0. Okay, so 0 1 1 0 was somewhere, like if you see here, this was a 0 0 1 1 0, and simply just try to rotate it, and then you will get all the codes, and that is why we are calling the cycling. So I think there is no need to discuss how it looks like. It looks like a cycling, because we need to get the code for this gray code just after rotating, like it is following the pattern just like a rotation. That is why we can call it a cyclic code. Okay, Yes, it is really important. Like this particular code does not exactly look like a cyclic, like what we discussed before, 0, 0, 1, 1. Let us assume I have a code. So I need to make it cycled by 1, like 1, 0, 0, 1, or something like that. This is not exactly looks like a cyclic, but there is some rotation in the code. That is why we can call it the cyclic kind of code. Okay. So this is not just like we discussed before. The significance of the cyclic code is sometimes in the arithmetical operation directly, without any operations, you can do some arithmetical operation like multiplication or division. How it could be done, I will tell you later on when I will talk about the Boolean algebra. Okay, this is really very good question. Okay, suppose you have some number and you are rotating by some bit. Okay, if we are rotating in left or right direction, that may treat as a multiplied by 2. Why? How it is so? Let me tell you. Suppose I have a number something like 0, 1, 0, 0. If I rotate this bit in the left direction, then it will become 1, 0, 0, 1, 0, 0, 0. The equivalent of this one is 4. The equivalent of this is 8. So what it means? I am multiplying by 2. Similarly, if I am rotating in the right direction, then this will become 0, 0, 1, 0. Okay. And if you see, this is nothing but this is equivalent to 2. And if it is equivalent to 2, what it means? We are dividing by 2. So this is the simple, like just by rotating, you can do some multiply by 2 or divide by 2 operation directly. Is doubt is clear? Your doubt is clear now? Yeah, I was about to say later on, but yeah, now because you asked the question, that then I have answered. Perfect. Fine. So this is all about the gray code. Now let us try to use this gray code for something. Like suppose I have a binary code, okay, and I want to convert that binary into the gray code. So how we can do that? How we can perform the binary to gray code conversion kind of operation? Okay. So to perform that one, what I have to check and what I have to do. This is really very important. Okay. So let us try to understand that one. Suppose I have a binary number which is starting from the MSB is the BN and the least significant bit is the B naught. Okay, so it is BN to B naught are the binary number, where this is the MSB and this is the LSB. Okay, and suppose I have a gray code that is represented with the GN to G naught, and the GN is the MSB and G naught is the LSB. Okay, so how we can convert the binary to gray code? This is really important. Okay, so to convert binary into gray code, we have to follow certain regulations. What that regulation is, if whatever the BN I have, okay, what is the most, I have to start with the most significant bit. Okay, so whatever the number I have at the most significant bit side, I have to replicate it as it is. So there is no change in the most significant bit in binary or in the gray code. Whatever the binary code I have and whatever the most significant bit I have in the binary, that will be same as the most significant bit for the gray code. Okay, this is the first thing. Second thing, now how I will calculate this GN minus 1? It is not like just I have to replicate each and every one, otherwise it will become the binary one. So I have to do whatever the most significant bit I have, that most significant bit, and the next most significant bit, like BN and BN minus 1, I have to perform some operation behind this one, between this one, and that operation is the XORing. I have to XOR BN and BN minus 1, and the result will be reflected as GN minus 1. Similarly, if I have to calculate GN minus 2, then I have to XOR the BN minus 1 and BN minus 2. This is the symbol for XORing, right? And then that after XORing, whatever the results I will get, that will become the Gn minus 1. And similarly, similar kind of concept we can utilize for other things. Similarly, for here, B1 and B0, I have to XOR B1 and B0, and the result will become G0. So this is the binary to gray code converter. In simple word, you can write something like it in mathematical way, like Bn XORing with Bn minus 1, and that will give you the Gn minus 1. Okay, so where this, let me, instead of n, because I have already used n, so Bi, I, and here Gi minus 1. Okay, here I is equal to n minus 1, and this is up to 1 to 1, something like that. So this is the mathematical way to represent this one. Now let us take some example so that you will be able to understand what I am saying. Okay. Yeah, of course, one more thing, like this formula is valid for the, not for the most significant bit, because the most significant bit is as it is, which we are replicating. So this is valid for the other bits, not for the most significant bit. Okay, so let us take some example and try to solve something. Suppose I have a binary which is 1001. Okay, let us assume I have a binary which is 1001. This is in the binary, and I want to convert into the gray code. So can anyone tell me what will be the gray code? Ajay, do you know what how this XOR operation works? So before that, I need to explain how this XOR operation works. Okay, so XOR operation is simply just like, suppose I have two inputs, A and B. Okay, and if I am XORing these two, A and B, okay, so what will be the output? So the output, let us try to see what is the output. Let us assume I have a 0 0 0 1 1 0 and 1 1. So the property of XOR is that gives logic 0 if the number of ones are even. Okay, so 0 1 1 0. For odd, it gives logic 1. So this is the truth table for the XOR. We will discuss it later on in more detail. For now, just try to understand. For the XORing, I have to just follow this kind of truth table. Okay, so for 0 0, it will give 0. For 0 1, it will give 1. For 1 0, it will give 1, and for 1 1, it will give 0. Okay, so can anyone tell me what will be the gray code for this code, whatever we have written here?
Sir, 1101.
1101. Perfect. So 110 is absolutely correct. So let us try to see how it is 1101. Okay, so gray code. Okay, so let us try to see. The most significant will be as it is, just like a binary. So 1. Now I have to XOR this 1 and this 0. So 1 and 0 XORing, if I'm doing, so that will give you the 1. Okay, so I'm getting 1. Then I have to XOR 0 and 0, that will give you the 0. And then I have to XOR 0 and 1, that will give you the 1. So this is how the gray code looks like. Okay, so the binary to gray conversion is very easy, not tough. So just you have to follow the same kind of whatever we discussed. Suppose I have to make a circuit for this. Okay, I have to make a circuit that I'm giving the input as a binary, and I just wanted to take output as a gray code. So what kind of circuit could be? See here, the most significant bit we are just transferring as it is. Okay, so the how it will look like, B3 will be same as the G3. Okay, so this is what I will get, the B3 if I have a 3-digit like a 4-bit number. Okay, now if I have to calculate the G2, then what we can do? Can anyone tell what we need to do? Let us assume to get the G2, I have to XOR the B3 and the B2, and in result, I will get the G2. Okay. So the most significant bit and then the next B2 that I need to XOR it, and I will get the G2. Similarly, if I am XORing the B2 and the B1, I will get the G1. And if I'm XORing the B1 and B0, I will get the G0. So this is the simplest circuit that will convert the binary code to the gray code. Yeah. So this blocks is nothing but this is the binary to gray code converter circuit. Later on, we will see how we can design this circuit. Just now, I just told you how we can do that. But to understand it properly, we must know how we can design these kind of circuits. Okay, so this is really important. It's not like just based on the logic you can do it. You should know the concept how we can design this kind of circuit. So this is how we can make the binary tree to gray code conversion. Similarly, suppose I have a gray code number and I want to convert the gray code to the binary. So how we can do that? Okay, so suppose for gray code, I have a number like Gn to G0, just like we did for in the previous slide. And I have a binary which is the Bn to B0. Okay, then what is the process to do that? To do the process to do that is simply, let us assume this Gn is the most significant bit and the G0 is the least significant bit. Okay, now what I have to do, whatever the MSB I have, because see, the MSB for gray code and the binary code is same, so this will be reflected as it is. So the Gn is same as the Bn. Now if I have to calculate the Bn minus 1, what I have to do, I have to XOR the Bn whatever I have received with Gn minus 1. This is the XORing, and whatever the results I am getting, that will be reflected as a Bn minus 1. Okay. Similarly, whatever the Bn minus 1 I have, that number, that digit will be XORed with the Gn minus 2. Okay, and whatever the results I will get, that will be reflected at the Bn minus 1, and so on. I have to follow the same kind of process. So for B0, I have to XOR this B1 and the result B1 and the G0, and the result will be B0. So this is how we can do that. If we try to write it mathematically, we can write it like for the other than this MSB, Bi XORed with Gi minus 1 is equal to Bi minus 1, where I is n minus 1 to 1. Okay, so this is the formula that we should consider. Now let us take an example. Like in the previous slide, we considered the binary was 1001 and the gray code was like 1101. Okay, so let us consider the same example which we calculated and try to do it in the other way. Like I had a result like 1101 was the result in the gray code. Okay, so let us try to write it. Okay, so binary gray code is 1101, and the binary is, what is the binary? Let us try to see. MSB will be as it is 1, and the next bit will be like I have to XOR this 0 1 and 1, and 1 and 1 XOR gives 0. We saw in the previous one, so that will give you the 0. Then this 0 and this 0, that will give you the 0, and this 0 and this 1, that will give you the 1. Okay, so this is what I will receive as a binary code. Okay, if I have to make the circuit for this, so the circuit is just like before we just discussed. G3 will be transferred as a B3, and if I have to calculate the Bn minus 1, or the B2, I have to XOR the Bn or the B3 and the G2. Okay, so B3 and G2 will be XORed, and that will give you the B2 result. Now, suppose I have to find the B1, then I have to XOR the B2 and the G1. So the B2 and the G1, like I have to XOR the B2 with the G1, and that will give you the B1. And similarly, if I have to calculate the B0, then I have to XOR B1 and G0, and that will give you the B0. So this circuit is nothing but gray to binary code converter. So is there any doubt on the binary code converter or this gray to binary and the binary to gray code converter? In case any doubt, you can ask the questions. Otherwise, we can move ahead with this one. So this is the simple thing that we can do, right? So it's quite easy, not that much difficult. Okay. Now let us further move ahead with the next kind of code, and that code is the alphanumeric code. Okay, what is the alphanumeric code and why it is needed? Okay, so alphanumeric code is nothing but, suppose if I am talking about some number where the alphabets, like if I'm talking about some code where alphabets and the number and the special characters are present. So to represent those numbers, I need the alphanumeric codes. Okay, so basically alphanumeric code is utilized where we have both kind of things, like the numbers, alphabets, special characters. So to accommodate all these symbols, we need to utilize the alphanumeric code. Basically, there are two types of the alphanumeric code. The first one is the ASCII code. ASCII code means American Standard Code for Information Interchange. The full form of this ASCII is American Standard Code for Information Interchange Code. Okay, this code, yeah, the full form is also written here, and this code is the 7-bit code. Okay, and the total number of symbols, like because we have the 7-bit code, the maximum number of possible symbols are 2 to the power 7, which is 128. So we can accommodate up to 128 symbols. Okay, so out of that, like A to Z could be there, small a to small z could be there, then 0 to 9 could be there, some other special character could be there. So maximum number of symbols that we can accommodate is 128. Okay, but in some case, might be you have the more number of symbols, especially in the IBM processors, early IBM processors, where the number of symbols was more than 128. So in that case, we need to have one more or different kind of code which has more capacity other than this 128. Okay, and for that purpose, the second kind of code comes, and that code is the ASCII code. The ASCII means the extended binary coded interchange code. Okay, the full form of this is extended binary coded decimal for interchange code. The length of this is like 8-bit length was present in this ASCII code, and the total number of possibilities that we can accommodate here is 2 to the power 8, that is 256. Okay, so if we have more number of symbols that we need to accommodate on any code, in that case I have to use this ASCII code. Okay, so this is the importance of alphanumeric codes like ASCII and the ASCII code. Quickly let us go through the ASCII codes, like how they looks like. If we talk about the ASCII code, these are some symbols. This is the most significant bit and this is the least significant bit, and these are some symbols. Let us assume I want to write the code for A. Okay, so for A, I need to consider where is the MSB and where is the LSB. So this is following this MSB and this is following this LSB. So what I have to write? I have to write first the MSB, which is 1 0 0, and then I have to followed by the LSB, that will be 0 0 0 1. So this code is for A. Okay, so this is how we can generate the code for different alphanumeric and the symbols. Okay, similarly, suppose I want to get the code for this end symbol, then I have to go with this one, which is the 0 1 0, and then in this direction, which is 0110. So this code is for the AND operator. Okay, so this is how the ASCII code works and how the 7 bits are responsible to generate a particular code. Means if you are pressing some key on a keyboard like A, what it means internally, this code is going like this is nothing but this is a binary kind of, and this the computer can easily understand this 10000001. Okay, and this is how we can interpret. So this kind of codes are basically the interface between human and the machine. Okay, both can understand the things. Okay, so this is how the ASCII code works and how it looks like. Just like the ASCII code, the ASCII code is also just like that, but in MSB and LSB we have the 4 digit on each side. Okay, so the ASCII code, if we have this is the most significant bit and this is the least significant bit. They have given in the hexadecimal pattern. What it means, this is the 0000 and this is nothing but this is the 1111. Okay, and similarly, suppose I want to get the code for E. Okay, so what I have to do, I have to check what is the most significant bit, which is C, and I have to find the equivalent binary code for the C and also for equivalent for 5, and that will become the ASCII code for E. Okay, and this is how you can get the code or the ASCII code for the alphanumeric symbol or some special commands as well. So some special commands has been added on this one. Okay, you can see some of the combinations are not is being used. Okay, just like if you see here, this one, some of the combinations are not used. Okay, so because these are reserved in case if you have more number of commands, more number of symbols, you can accommodate these or you can assign these codes for those commands. So this is what the ASCII code is. So you can create your own code, your own combination of bits to get the different